everybody. Welcome to EC 5233 Satellite Communications course. This is a graduate course here and mostly taken by wireless students. What I have handed out is syllabus for the course, and it kind of gives you all the vital information about the course itself. I'm going to walk through this and try to explain as much as I can right now, and kind of give you a good insight of what the course is going to look like and what does it take to successfully complete this course. The first information that you have up at the very top are the information about myself, my name, and the email address, the phone number. What you don't see here is my office is on the third floor, room 304, right? So, and I hold office hours every Tuesday and Thursday between 2 and 5. So those are the times where I'm pretty much guaranteed to be there. I'm there other times, but I do other stuff too. So if you need to see me outside of the office hours, send me an email and we'll schedule a time. What is important here is this URL that you see on line 4. This gets you to the Wireless Center of Excellency webpage, WICE. And this is our web page, and you can see the tabs here, but what is important is this tab that you have linked to all the courses that I teach, and this is where I post all the material related to this course. What you're going to find there are several things. You're going to find all the PowerPoints that I use for the class. You're going to find all the notes that are associated with the class, all the I guess stuff that I write, and all the examples that I do, and all the derivations, because there's just a limited space on the PowerPoint when it comes to presenting math, right? It's not very good medium. So all the important derivations and examples you're going to find in the notes, and notes are more comprehensive than what I did on a PowerPoint, so you're going to just have the highlights here. Now, for the first time this year, Masood and I will be filming these lectures, and we're going to be posting those lectures on this website. Now, it's the first time, so it may be that they're not available right the same day, but within a couple of days we're going to be uploading them to YouTube, and you're going to be able to see pretty much what I cover in class. And I found I do that with other classes, and a lot of students find it beneficial, and I see them every now and then watching those videos. I think it's extremely beneficial because a lot of you travel, a lot of you are maybe not able to make it to the class, so that kind of tells you exactly what happens in the class. Now, for some of the lectures, there will be some additional videos that I plan on posting. There's actually just 2 lectures of that nature. One is the second lecture, the one that is going to be this Thursday. And the reason why I'm going to have additional video, this one is very math intensive. It actually, I go through the derivation of what is called a two-body problem. And it's just a whole bunch of differential equations. I would like you to go through it to understand where all these Kepler laws are coming from. But I felt like it's kind of too lengthy to cover in a single class period, and I didn't want to stretch it over 2 class periods. And there is also additional video that you can see this in the class period 10. We're preparing for this class. There's a section where we talk about what does it take to build a satellite. And I started putting all the stuff together, and then accidentally I stumbled upon a YouTube video put by BBC out that actually covers this exact topic. They go to a satellite company and then go through all the processes that it takes to build a satellite. And I thought that this was done much better than what I would have put together. So one class period, we're just going to watch YouTube for 55 minutes. How does the class work? The book that I'm going to be using is this book. That's a book by Pratt, Bostonian, and Allnut. It's an excellent book. Despite being a little bit old, what it does, it actually covers the fundamental of the satellite communications that haven't changed much. You know, there are all these signal processing techniques and all of these relative new developments that are now implemented in satellite communications. There are new frequency bands and so on. But the principles haven't changed much, and they're covered to, I would say, in an excellent manner in this book. The book is also very good because it has plenty of problems, you know, that I'm going to be covering in class and that I'm going to be drawing from for all of your tests, right? So there will be a lot of problems that are going to be just positive. There are going to be a lot of problems that you're going to be doing in this course. Just like any other course I teach, it's going to be centric on you doing calculations, right? And there will be a lot of those in this course. Now, there are 31 class periods in the spring semester, and I kind of, in this table that you see here, outline what I intend to cover in each one of the class periods. You can see we're going to be covering chapters 1, 2, 3, 4, 6, 8, and partially 9. These are the chapters directly from the book. What I have done here is it is not possible in a single semester to cover, you know, entire or I would say entire content of this book. The book is larger than what would fit in one semester. So what I did is I tried to extract the things that are pertinent to satellite communications, and you know, the rest of the stuff is going to be covered elsewhere. Like for example, there's a good deal that this book spends on modulation and demodulation. We covered that to even greater extent in digital communication class. There's a good deal that this book spends on error control coding. We have a separate class for error control coding. So whatever is not, this book even covers FM modulation, because that used to be one of the dominant ways how we send the signals through the satellite. That's covering communication theory. So the stuff that we cover in our other classes that I know wireless students take is I kind of omitted from this one and focused on only the things that are really truly satellite communication things. So what are we going to have? The first part of the class, essentially after this brief introduction today, we're going to look at into orbital mechanics. Satellites are traveling around the globe, and even though we don't have to become physics major to know every single detail of it, you have to have a good awareness of how mechanics of this works, right? Because it's a part of dealing with the satellite. So we're going to be talking about Kepler's laws, Luke angles, how do you actually determine where the satellite is, and how far it is, what is its velocity, and implication that this has on our ability to communicate with the satellite. The second section here is what is in chapter 3. The satellite is a very complex structure. We are in this course interested only about a part of it, which we usually refer to as a payload, namely the electronics that facilitates the communication. There are all sorts of other things that are flying on the satellite that make this payload work, right? For example, there are systems for heating, for cooling, for stabilizing of the satellite, and all sorts of stuff that come with the satellite that makes the whole thing work. Now, talk about how you launch the satellite, what are typical launches, and what are some trade-offs that we have over there. That's going to be covered next. The big part of this course is link design. Link design is a set of procedures that we implement to make sure that we can talk to the satellite reliably, and that the satellite can talk back to the ground in a reliable fashion. So here we do all the propagation modeling, all the link budget analysis, antenna selection, all the calculations associated with the link design. Some of you went through the PCS class. It's very similar to the link budget that we do over there to make sure the coverage of the cell site is of a given reliability. Now, when you do calculations, you have to realize that the environment between what is in between the satellite and the ground changes. due to all the things that are in between, namely all the meteorological stuff, atmosphere, and so on. So your losses associated with this propagation are going to change. In a good design, you have to provision for those losses and make sure that you design your link with great reliability. That involves calculation of your design margins, and that's what we're going to learn in Chapter 8, how to calculate these design margins, what happens when it rains, how do you calculate reliability for various regions of the world, and so on. After that, we're going to be talking about multiple access schemes. This is the very similar talk that we have in other communication systems, but now looking at specific satellite environment. What does it mean to have a TDMA access in satellite? What does it mean to have a CDMA access, and so on? And then the last section that I'm going to dedicate to is to VSAT, very small aperture terminal satellites. This is one specific application. In your book there are 3-4 of these applications. They talk about mobile satellite systems, they talk about GPS system, they talk about VSAT. I just selected one of them to cover for the course, just to go through some of these processes once again for that specific scenario. Now, what you probably noticed, there are 5 tests in this course. Namely, after every significant section, we're going to be problem-solving session where I'm going to be going through the problems, just solving them on the board and discussing what, just how do you do the calculations and what do they mean. And then there will be tests covering particular section. I have pretty much limited the test to the previous section. The section on Chapter 3 doesn't have a test because it's mainly just a story of how to build a satellite, and it's there to build your awareness of what are the things that go into that process. But for any other section where there is some calculation, namely some engineering to be done, there is an associated test. And we're going to be doing tests here, and basically that's how your grade is going to be formed. As I mentioned at the very beginning, book is your best friend. I mean, no matter, and I'm not afraid to say that in front of the camera, right? Even the best instructor is worse than a worse book, right? Your book is excellent. So whenever in doubt, go to the book. It has pretty much all the material covered. It has an extensive list of references for anything that is mentioned in the text. And what is the most valuable to you, it has probably after every chapter, maybe 30, 40 different problems, that help you exercise the material covered in the chapter. You have to try to do all of these problems, right? All of them are very good. This is the second edition, so it's expanded based on what was already in the first edition. The first edition was excellent as well. So try to do all of those problems. Subset of these problems I'll try to do here in class, either through exercises or through a specific problem-solving sessions. But this is where your tests are going to be taken from. I'm going to be probably taking some of these problems, changing them a little bit, usually simplifying them because they tend to be lengthy, and this becomes stuff that you are tested in the test. So don't wait a minute. Whenever you're studying, do these problems. They will help you understand the material best. Each test is 25 points, so 5 times 25, 125 points for grads. Above 90 is 8, and that's standard scale after that. So, as we move through the course, you're going to be pretty much aware where you stand, right? Based on your tests and how you accumulate the grade. This last test is probably your final, so there's really no midterm. There's just all of these tests that are distributed throughout the course. So that's about the syllabus. Any questions about it? Any concerns?
Is the last exam commutative?
No. At this point, I left it open. I don't know. We'll see when we get there. This is the first time I'm teaching this course in this manner. This table might be ambitious, right? We may not get to the 29 and 30, right? Lectures, because stuff happens, we get delayed. But my hope is that we're going to cover all of this. Maybe we cover more. Maybe we luck out. But when the final comes, I'll probably decide what is going to be the final. It's not going to be cumulative because it's too much to keep orbital mechanics and But link design and margin calculations and elements of the access schemes are important things, to take away from the schools. So we'll see. We'll make the decision when we approach the finals. Any other questions? Go ahead.
Each test, is it open book or not open book? Open notes?
No, what I found out is that open book, actually, when I look at I have now significant statistics over the year compiled, and I saw that when I give tests open book, the results are far worse than when I actually make students, aware that it's not going to be open. So the tests are not going to be open book. As far as the formulas, I might actually give formula sheet or allow you to compile them. But we'll come to that point before the test. My inclination is not to give them open book, because what actually happens, it gives you a false sense of security, and you try to study on the test, and what happens, you run out of time before you tackle the first problem. So I want you to study and be prepared and compile your formula sheets and kind of organize everything before the test. Anything else? Okay, there are some. Do you all have the syllabus? A few more. The material that is right now on the website is the material that is from when I taught the class previously. So it's not 100% what I'm going to be presenting here. Be patient, because I'm uploading them as I modify them. By some reason they time everything will be there. But right now is previous version, which is basically what I'm working from. So it's, let's say, 90% the same. There are some new things that are introduced this time that are not there at this point. Okay, so that's as far as introduction. This is the first class, so we're going to go a little bit light today. What I'm going to talk about is just essentials here. So let me kind of give you a big picture here. So what are satellite systems? They are systems that allow us to communicate over large distances using satellites that are orbiting around the globe. Typically, when you look at a satellite system, there are two types of components that you identify right off the bat. There is something that's called ground segment, which consists of all the equipment that you have on the Earth, and there's a space segment that consists of one or more satellites that are responsible for all the communication that happens in space. Now, it used to be that space segments consisted of a single satellite, so you would send a signal to a satellite and it will be relayed back to the Earth. There are commercial systems right now that use multiple satellites, so we're kind of moving slowly towards network in the sky concept, where you're going to have the network on the ground that you call ground segment of the satellite system, and then network in space that is called space segment. Here you have a typical outline, one of possibilities for a satellite communication system. This is an outline just so that we can discuss various components. This is an outline of broadcast system, or system where you have many user terminals that are connected to a single central hub and to a single satellite. What would be an example of a system that works like this? Would be your satellite TV, right? You have a ground station that is connected to internet or some sort of data center that through a central ground station sends the signal to the satellite. Satellite acts like a repeater. It will receive that signal and broadcast it down to the Earth. And at the Earth, you have many users that are within the coverage area of the satellite that are receiving that signal and getting its content. As I said, the example of that would be your TV distribution Other examples are possible. I assume that these terminals are mobile, then you have mobile satellite system, right? That, for example, covering your airplanes or covering vessels or vehicles on the ground. The important part here, and this is where we're going to spend a lot of our time, are these links, right? The satellites are very far, right? If you think about, let's say, geostationary satellite, you're around 40,000 kilometers above the Earth. So these distances are large, and in radio propagation terms, large distances means huge losses, right? The signal that you send from the ground by the time it reaches the satellite is very attenuated. So what that means, you need to carefully design this link, make sure you select the antennas properly, make sure you take into account, you know, all the components along the way with the atmosphere itself. So we're going to spend a lot of time understanding how you design these links from the ground station to the satellite, and then from the satellite down to the ground station. That's pretty much our entire chapter 6 and 8. Now, here's a ground segment. What is on the back of this particular antenna? This is an example of a large, you know, the satellite antennas are usually dish antennas because they have, I guess, very high directivity, ability to focus energy in a single, in a small area of space, which we will see later. That is kind of pretty much equivalent statement as saying that these kind of antennas typically have the highest gain. So you have an example here of a satellite dish that is pointed towards the satellite. What is behind that dish? You have some sort of connection to the landline networks, and they can be over, as you probably know, over two kinds. They can be data networks, which in today's world means internet, or they can be telephone networks, which is our circuit switch telephony, where the former one is actually taking over, and pretty much almost all of our traffic is moving towards the data networks, even in the satellite arena. So that's kind of this comes to some sort of data center or some hub that we have on the ground, and then what happens is there is what we refer to as access scheme processing. What happens is satellites are rarely serviced by a single hub or single ground station. They usually have ability to talk to multiple or receive signal from multiple points on the ground. And whenever you have multiple endpoints talking to the single point, then you have a problem of access, right? How do you share these resources on the satellite so that everybody on the ground gets their fair share? So there's a certain amount of access, there's quite a bit of, I should say, access processing here, where you kind of assign the time slots or codes or frequencies to the ground station. And then after that, it's pretty much the regular communication, digital communication story. You have to modulate your signal on a frequency of the carrier. You have to upconvert to whatever is the frequency that you use to communicate with the satellite. You have to amplify it, send it to an antenna. There's a whole bunch of filtering, data conditioning that comes along here. This is very much the simplified diagram. On the reverse, the situation is kind of the opposite of what you have on the transmit side. You're going to be receiving signal that is very weak that comes from the satellite. This is the link from the satellite to the ground is the one that is always the most, I guess, problematic in the sense that it has to be designed in the most detailed way, because when you're up in the space, your ability to amplify is limited because you're limited by how much of the energy you can harvest from your solar panels or whatever is the means that you use to generate your energy. So the signal as it comes to the ground station is very weak. It needs to be carefully amplified through what is called low noise amplifiers. These are the specifically designed amplifiers with a very low noise figure so that they can detect this weak signal. Then the signal is down converted, demodulated, and then demodulate your part of it. If you're in some sort of access scheme, not everything that comes from that satellite is meant to you, right? Maybe you're only listening to this particular time slot and the rest is going to the other users of the system. And then after that, it kind of goes to the rest of the network. So if you think about it, what satellite is, it is essentially a repeater, right? It's a equipment that allows you to communicate over large distances. Sometimes you will hear people refer to a satellite as a bent pipe, meaning because it's a data pipe that is kind of bent through the satellite, right? We'll talk about that term, and you will see that it's just covering some types of satellites. There are different types of satellites that one of them are bent pipe satellites. So that's a ground segment. Space segment. This is essentially your satellites. They consist, as I said, of two things. They consist of a payload and a platform. Payload, when you say the satellite payload, this is the electronic equipment that exists on a satellite that justifies the existence of the satellite. This is why we have that satellite, is to carry that payload. In our particular course here, all of our payloads are going to be communication equipment, right? The equipment that allows you to communicate. That is by no means the only type of the payload. You have the satellites that are there for remote sensing purposes. There are satellites that are surveying meteorological satellites. There are satellites that do all sorts of things where the payload is whatever electronics you have on there to do this particular thing. There was just a couple of weeks ago here a presentation about the satellites that are measuring salinity of the ocean. So what they do is they just take a very careful temperature measurements, that are within a 0.1 degree, right, of the surface of the ocean, and then calculate what the salinity is and so on and so forth. So in that case, you're not communicating. The payload are all the sensors that are on that particular satellite. For our course here, we're going to be concerned about the satellites that are there to facilitate the communications. Besides the payload, there's a platform, and there are all sorts of systems that exist on the satellite that help this payload work. There has to be something on a satellite that generates the power, right? Because everything requires energy to work. So there will be solar panels or some other means of generating the power. There are going to be systems that are responsible for the satellite to stay at the proper spot of the orbit. So there are going to be actuators and different telemetry things that will make sure that the satellite doesn't drift out of the orbit. And there's all sorts of other systems that facilitate the work of the payload. We're going to mention them. It is not part of this course to deal with them. We're not, I guess, communications engineers, so that kind of belongs more in a mechanical engineering. So here, our payload is going to consist of a receive antenna. We're going to be talking about both receive and transmit antenna in our calculations. There will be electronics that are designed to do the communications, and the transmit antenna that is sending signal back to the ground. And in all satellites that are designed for this purpose, the frequency of the receive and transmit are different. So what the satellite does, it receives on one frequency, processes the signal, and then transmits on the other frequency. In all applications that I know of, the uplink frequency is higher than the downlink frequency, and this is, you probably understand why that's the case, because when you go lower in frequency, your propagation is facilitated, right? Because your losses are going up with 20 dBs per decade as a function of frequency. There are two types of satellites that are deployed for communication purposes. The first type here that I have on the first drawing up there is called bent pipe satellite, and that's a traditional way how the satellites are designed. In this case scenario, your satellite is truly a repeater. It receives a signal within one frequency band. It takes whatever it receives there, it amplifies it, down converts it to a lower frequency, and sends the signal down to the earth. it has no knowledge or concern what that particular signal is, right? Whatever falls within that band of interest will be amplified and retransmitted, down converted to a different frequency and retransmitted down to the ground. So it's what we call translational repeater, or in this case, pipe. Now, typically what you find out is that there are multiple channels on every one of the satellites. Channel in satellite terminology is assigned to a set of electronics that we call transponder, right? So you can think of pipe satellite as a bank of the transponders, each one having its particular channel. So you may have, let's say, 24 transponders. Each one receives at a particular frequency. It takes the signal down, converts to a different frequency, and then sends that to the antenna. So, and then in this architecture, the minimum allocatable resource that you can give to the communication on the ground is a transponder. You can say, I have this transponder reserved for this particular time. Now, these are traditional satellites, and this is how the communication satellites were designed from the very beginning. You know, the beauty of this approach is it is somewhat future-proof, right? Because you're not really looking into your signal, and the signal can be anything. You can actually, within certain limits, change that signal without affecting the work of the transponder. Let me give you an example. Let's say this first satellite was designed to carry FM signal, right? And then at some later date, we discovered that digital modulation is much better than FM. Well, you can switch your modulation scheme to digital as long as you're within a certain dynamic range. You're okay, right? Because the satellite does not care what kind of modulation. As long as it receives a signal, it's within a certain power limits, and it doesn't saturate whatever it is not supposed to saturate. It will retransmit the signal back to as if it were designed to carry that signal in the first place. Now, what we are seeing as of recent years is another generation of satellites that are called satellites with onboard processing. Now, here, what happens is you still have a notion of the transponder. There is a reception of a given channel, but at this point, the satellite, actually demodulates the signal. It goes all the way from the RF frequency to the baseband and gets back ones and zeros that were sent from the ground. Now, by doing so, let's say, and with enough error control coding, you're actually cleaning up your signal, and you have a possibility to do two things. First one is, if your uplink is strong enough, which usually you can make it strong enough with this essentially very high powers from the ground, then you can you're essentially link that is the only link that is exposed is your downlink. Just like in the case of the terrestrial communications where you have the repeaters, you're pretty much cleaning up all the noise that is accumulated between each repeater hop, right? So you get rid of the noise and you regenerate the signal, and if you didn't make any errors, it's just as clean after the first repeater than as it was when it was sent at the very beginning. So by doing so, you have your link budget advantages. But what this also allows you is, since you brought your signal back to the baseband, you can do what is called switching in the sky. And this kind of architecture goes with the satellites that actually have some routing capability. So, for example, you can send, let's say, one composite link to the satellite, and the satellite can have two antennas that can recognize that this portion of your traffic goes this way, and this portion of the traffic goes this way, right? And you can do this kind of switching. And there are some satellites that are operating in this fashion. Problem with this is these satellites, once you design them, they're kind of, bounded by whatever modulation scheme and whatever processing you originally put in them. So if it is designed, let's say for the sake of example, if it's designed to demodulate QPSK, you cannot switch now to a completely different modulation scheme without, you know, even, I don't know if it, you cannot really switch, right, unless you have some way of reprogramming the satellite and changing the components and so on, which usually you don't have. Once the satellite is in the orbit, nothing really fixes it, right? It goes broke, it just falls down to the earth. However, in recent years, what we started doing, and this is a very active area of the research and where this whole technology is going over the next few decades, is there is something called software-defined radio, which is essentially a radio that has ability to reconfigure itself based on the software. And then these radios are kind of seen as a future for the satellite communications, where you can use the onboard processing, but as your needs change and your waveforms change, you can actually reprogram the satellite to accommodate for these changes. That's an active area of the research, and there's a big drive to actually do some standardization in this area, because right now it's at the very beginning and a lot of that development is still ad hoc and left to the individual space satellite manufacturers.
I know this one guy, his dissertation was on sending, he had like an FPGA on board.
Correct.
So you would uplink basically pieces of code onto and reconfigure the FPGA to
Correct.
modify it.
That's exactly how it works. Right now, I don't know if you know my student Jeff White. He's my PhD student. We actually have a grant from Harris where we do exactly that. There's a software radio that is flying on International Space Station, and we're now reprogramming it to do adaptive single carrier or FDMA single carrier or FDM modulation scheme. So and this is exactly, but the point of this whole exercise is for us, I guess it was the solicitation by NASA, and one of the goals of this whole exercise is to bring the readiness of the technology to the next level, because we all recognize that this is still in its infancy, and we all need to kind of agree how this is done, right? Just like we did that with the satellite communication, where we have an extensive standardization and we understand how we advance the technology. The same attempts are made here. Okay, so that's space segment a little bit, and then the next thing is end user segment. The end user equipment comes in all sorts of shapes and forms based on how these services being provisioned. You have what is called fixed satellite services, where I don't really have here an example of that. There are fixed satellite services are where the satellite link is part of some backbone, right? You have huge aggregation of traffic on one end, you have a big hub on the other end, and you just send the traffic from one side of the globe to the other side of the globe between two fixed Earth stations. So this is what we call fixed satellite services. Then you have all sorts of mobile satellite services where you can have, you know, if you are on a sea above the ocean somewhere, your only way to communicate is satellite. So all of our vessels that are either flying or you know, floating on the sea are equipped with some sort of satellite communication systems. We have what is called satellite on the move, where you have a lot of vehicles operating satellite systems. You know that this is not anything new. For example, GM cars have OnStar systems that allow you to unlock your car through the satellite link. Then there's also there are some commercial systems that augment your cellular systems. If you are, for example, Verizon subscriber, you can get Globestar phones that will allow you to have your cellular service when you're not on land, when you're outside of the coverage area of cellular terrestrial network. So these are all what we call mobile satellite services. Their signature is that your user terminal is mobile, right? So you are kind of roaming freely within the coverage footprint of the downlink satellite antenna. And then we have also the broadcast satellite systems, like TV distribution systems that allow you to receive TV programs, and those are one of the, I guess, very commercially successful systems that allow you to, I guess, receive the satellite signal that is just being broadcast on the ground. As I say here, it can be user equipment, may be, as it says here, connected to the end equipment or part of the end equipment. Here is an example of those phones over there. The satellite receiver is part of that cell phone, but here you have a satellite receiver that connects to your television set that allows you to view the program. Now, as you know, satellites fly around the globe, around the Earth. And based on how high the satellites are above the surface of the Earth, we typically talk in terms of three satellite categories. We talk about low orbiting satellites, medium Earth orbiting satellites, and then geostationary satellites or geosynchronous satellites. How are they distinguished? Well, if your orbit, meaning if your altitude, the height above the surface of the Earth is below 2,000 kilometers, then you are in a low Earth orbit. Those satellites are very close to the surface of the Earth. What that means is the distances to them are small enough so that they can be reached with a relatively unsophisticated antenna systems that don't have much of a gain. If you're talking from your satellite phone to a satellite, your phone antenna is not very high directive antenna. It pretty much radiates in an omnidirectional fashion. Therefore, your satellite needs to be close to the ground. Now, what that means practically is those satellites are moving relatively fast to you as a user, and they're orbiting the Earth relatively with a short period. We're going to go into these calculations as of next lecture, but just for right now, if you are in a low Earth orbit, your speed is about 8 kilometers per second. This is the speed that allows you to orbit the Earth without falling on the Earth. And it takes about 90 minutes to go around the globe. So that means that satellite is zooming across the sky relatively fast. And if you want to have any considerable coverage, it is obvious that you cannot have only a single satellite. So when we talk about low Earth orbiting communication satellites, we usually talk about constellations. And we have multiple satellites that are carefully designed and arranged so that any given moment you have a visibility to one or more than one of those satellites. If you think about, I know a lot of you come from a cellular background, it's the opposite of the cellular paradigm. In cellular network, you have base stations that are sitting still, and you are moving and handing off from base station to the base station. In low Earth orbiting satellite scenario, you have a mobile that is pretty much sitting still, and called base stations that are now, going around, and then you're handing over not because you moved, but because the base station that used to serve you is now, over China, and you don't see it anymore. So that's how this one works. There are two systems that are famous, and I suggest you kind of Google them. One is a Globestar, and the other one is Iridium. Both of them are commercial systems, and they're low Earth orbiting satellite systems. Globestar has 48 satellites. Iridium 66. Now, if you move above 2,000 and all the way to 35,786, that's that magic number, and I'll explain what it means. But in this range, we call satellites medium Earth orbiting satellites. And you can see here the velocities are between these 8 kilometers and 3 kilometers per second. Orbital periods are anywhere from 2 to 24 hours. And there are the best example of this system is the GPS system put in space originally by U.S. government. It's a constellation of 24 satellites that are orbiting the globe, and with the idea that at any given instant, from any point on the globe, you have this ability to 3 or more satellites. And these satellites are not really communication satellites. What they're sending are the beacon signals that you can receive on the ground, and then knowing what those signals are and what the delays to these individual satellites are, you can actually calculate your position on the globe. And you know that this system is very successful. It started as a military system, but now it's one of the most successful commercial systems. Pretty much, it's in every modern cell phone, and there are a lot of other technical solutions that use the GPS as a source of timing, source of location, and whatever other use they need to get out of it. Now, if you move further out, you end up with satellites that are located at roughly 36,000 kilometers. Those are the satellites that orbit the Earth in exactly 24 hours. And 24 hours is, you know, how fast the Earth spins. So these satellites are synchronized with the rotation of the Earth. There are two kinds of satellites that are at this distance. There are satellites that are in an inclined orbit, meaning that their orbit is tilted relative to the equatorial plane of the Earth. So that means even though they are orbiting with a 24-hour period, because Earth rotates this way, they're not always above the same spot on the Earth, right? These are called geosynchronous satellites, and there are few of those, but not as many as geostationary satellites. Geostationary satellites are the ones that are actually envisioned first, and they are special in a sense that they are synchronized. They're all in equatorial plane, so they're all at around the equator of the Earth, and they're in this orbit that is synchronized so that their period is exactly 24 hours. So if you think about a globe and think about a satellite, and both of them rotating 24 hours, that means that the satellite from the I guess viewpoint from the ground is always in the same spot, right? If I'm sitting here and I'm rotating with the Earth, and the satellite is at this geostationary orbit, it is rotating at the same speed. This satellite is always at the same spot. And these are by far the most frequent communication satellites. And a lot of the material that we're going to be covering in this course is kind of geared towards those satellites. You know, you will see very soon, maybe in the next lecture, that unless it's geostationary, the orbital mechanics gets pretty heavy, right? And just we have to kind of resort to tools, and I'll probably show you a couple of those tools that help us calculate, you know, the exact position of the satellite. But for the satellite that is in a geostationary orbit, all you have to know is its longitude, right? You say this satellite is at 73 west. What that means it is always at this particular longitude, and then it kind of rotates with the Earth. And it's always above this point when you from the Earth. So we have three kinds of orbits: LEO, MEO, and GEO, right? And GSO is geosynchronous. LEO and MEO satellites are sometimes referred as NGSO satellites, right? No geosynchronized satellites. And in particular, that comes up a lot of time in frequency management documentation. Like if you read FCC stuff, they would say NGSO satellites. They would allocate the bands for non-geostationary and geosynchronous satellites operation. Now, these are different satellite services, and you know, again, for the purpose of licensing, the way how this is done I guess globally, you allocate the frequencies that you're going to allocate for satellite communication, and then for every allocated band, you specify what kind of services you're going to have in that band. And the reason for doing that is to make sure that these satellite services coexist. Like if you have the easiest one to manage are the fixed satellite services, right? Because you have fixed point-to-point communication and point-to-point down. So you're occupying relatively narrow portion of the space, and you can reuse these frequencies the most often because you have very high directive antennas and you're not polluting the large geographical area. But then you have mobile satellite services where, in particularly on the downlink, you're going to be covering the area. You say this satellite provides service in the continental U.S. That means everywhere in the continental U.S. you're going to hear the signal from the satellite. Another way to see that is if I allocate the frequency to that satellite, I cannot give it to somebody else, because if I give it to somebody else, they're going to interfere. Right? So you have mobile, then you have broadcast satellite services pretty much working in a similar way. Now, there are other satellite services that I list here in gray that you can look and realize that these systems exist out there. We're not going to be talking about them, except maybe mentioning them every now and then. I've kind of mentioned navigation satellite, Earth exploration satellites. Those are the ones that survey the Earth for different purposes. One typical example are the Google Earth maps that are now pretty much documenting every part of the globe. Space research services and so on and so forth, like all the satellites that are detecting the radiation, that are carrying various telescopes and all sorts of measurement equipment that help us learn about the universe. All right, so these are different services. For us, what we need to know is, as I said, is that satellite service comes with a given spectrum, and we talk about this is a satellite service in this particular spectrum, and then within a given spectrum, it needs to follow within a certain service category to be a valid license. This map here gives you some of the satellite bands that are used for communication. Now, in satellite world, we adopt what is referred to as military microwave frequency band designations. In other words, when we talk about satellite systems, we talk about L-band, S-band, C-band, and so on and so forth. Well, that nomenclature is not very fortunate for two reasons. First, it's a little bit loose, because if you look at KU band, for example, it says 12 to 18 gigahertz, but there are KU band systems that are 11 point something gigahertz. So these bands are not really very, very precise. And then, but they're kind of used to roughly tell you where the system operates. When in every one of these bands, you're going to have two frequency blocks, one allocated for the link from the ground to the satellite, and the other one allocated for the link from satellite to the ground. So if you, for example, let's say we pick up KU band, it says it's 12 to 18 gigahertz, but if you look at here, there's 14 to 14.8 gigahertz for the link from the ground to the satellite, and then there is it says up there, and there is 10.7 to 1275 for the link from the satellite to the ground, right? And this is kind of rough, and there's another layer here that kind of gives you all the detail about how various bands are being allocated. What you don't see here is that in some of these bands, what is specified is what kind of service you can have in this band. This is just frequency allocation cable. Now, what happens at this moment, what you find out is the most used bands are C-band and KU band. Those are the two bands that are used for commercial systems, right? Commercial satellite communication systems. X-band, at least in the US, is primarily given to the military, right, the government. So X-band is used by government. L-band and S-band are, as you can see, very, very narrow. I mean, what happens is when you go low in frequency, your bandwidth is also limited. So L-band satellites are navigation satellites. GPS is an L-band satellite. S-band are mostly used for surveying purposes. And the majority of the communication is done through either C-band, where most of your broadcast is done through the C-band and mobile satellite services, but primarily KU band is used for high bandwidth communication. As of recently, and I say recently, maybe last 5 years, there's an extensive development in the KA band, which, as you can see, is relatively high in the frequency. And there are a lot of satellites even being launched as we speak that are going to be operating in the KA band. KA band is attractive because it gives you quite a bit of spectrum. If you look at how much spectrum exists in the KA band, is probably more than all of the other bands combined. It allows us to, satellite services to compete favorably with even optical fiber in the sense that your cost per megabit can be relatively low. And there are a lot of, as I said, satellites that have been launched in this band. However, as you move higher in frequencies, you have to deal with higher propagation losses and the fact that your atmosphere now starts to matter tremendously. And we'll go through later in the course and talk about all the design issues that come with going with higher frequency. So just from this slide, these various band designators, and they're not easy to remember. At least for me, they were not easy to remember. Like, you always kind of say, well, what was exactly KU or what is exactly KA? But my hope is, by the end of this course, it becomes a second nature. Now, just a couple of words about how frequency is managed. There are globally, frequency is managed through ITU, International Telecommunication Union. This is part of the United Nations, right, ITU. And it is very easy to see that once you start talking satellites, once you look at Earth from the satellite, the boundaries between the countries do not really exist, right? So what needs to happen is these frequencies need to be carefully managed so that everybody has fair access to this, I guess, finite resource. From the regulatory perspective, we divide the world into 3 ITU regions. ITU region 1 is the blue one over there, and you can see it's essentially Europe and Africa, where we took Russia and it becomes a part of the Europe. So that's why a big part of the Asia is also blue. Then you have ITU region 2, which is 2 Americas, and ITU region 3, which is Asia and Australia. Even though there are 3 regions here, regions 2 and 3 are very close. There are very few differences between these 2 regions in terms of how they allocate frequencies. And for the most part, all 3 regions have the certain bands identified as the satellite bands. There are some minor differences, and the hope is that over time they're going to disappear, so we manage the whole world globally. Now, the frequency bands are allocated globally, right? So let's say you're operating in ITU region 2 here in the United States. So what that means is when I say KU band in ITU 2, that you can go to the table and find that this is from 14 to 1475 and from 11 whatever, exactly the frequency ranges and the amounts of spectrum that are given to the satellite service. But that doesn't mean that you can provide a service in a given country. Let's say you're a TV provider, satellite TV provider, and you broadcast the signal then even though you operate within the given frequency band, you have to have a license to provide the service in every given country. So let's say you broadcast the signal and it's a TV program, you have to still go to the government of the local country and become a legal TV provider in that place. And I don't know, you probably have heard that you can have this. You cannot really limit satellite signal to confines of a given country boundaries, right? So if I broadcast, let's say, satellite TV signal, it will cover the entire Europe. And if I don't have the license, let's say in Italy, I'm not going to be able to provide this service legally in Italy. But people can get a descrambler and usually, I guess black market and descramble the signal for free because it still exists there. So the bottom line here is you're broadcasting within a given frequency range, but providing the service is still under control of local governments. As I said, frequencies are in pairs, one for uplink and the other for downlink, and uplink frequencies always higher, just because this link has more power. I copied a few notes here from. There's a good section in the book that talks about history of the satellite. The first satellite officially was launched in 1957 by what used to be USSR. It was called Sputnik. It was relatively small, 83 kilograms. That's a little bit more than what I have. So it was relatively small. It went around, that's the picture of it, around the globe in a low orbit for about 3 months, and it actually didn't do much. It just sent a beacon signal that was received on the ground, and for the purpose of studying to see if something like this was even possible. There are two, as I say here, two fundamental components of the satellite technology that have to be developed for this concept even to become feasible. One is the microwave communication, and we developed that for radar systems and for all the terrestrial systems. And what you have in satellites is just very similar to what we have in the terrestrial system. When you talk about super high heterodyne receiver, its implementation in satellite is very close to what you have in your cell phone or what you have in your car radio. So that kind of technology was developed as a part of all the terrestrial systems. But what needed to be developed to actually make the satellites feasible is all the missile technology. It turns out, Earth is a pretty big place and it has a pretty significant gravity. And even today, to put something in space is not an easy task. We've been going for 40 years plus, launching various things, and every time we launch something, it's still pretty expensive. Right now, I think it's about $30,000 per kilogram of load to put into space. So if you have, how much you weigh, so you can calculate how much it will cost to put you in an orbit, and you can see that it's pretty expensive even today. Now, the first satellite that I said here was just an experimental satellite. The first commercial satellite was launched a decade later. It was something called Early Bird by Intelsat, and it was a satellite that connected Europe and America and allowed telephony, satellite telephony. It could handle 240 voice channels and 1 TV channel, and this is how it looked like over there. This is essentially the first commercial satellite, telecommunication satellite, where you can actually make the phone call through. It was launched from Kennedy Space Center, so I feel kind of a little bit honored because it's just a few miles from here. Now, since these early days, the satellite industry went through several stages. And I took this from a different book, but I found it pretty instructive here. We have first stage that we call imagination, right, where we actually
started for the first time realizing that this is possible and trying to put a bounds on what sounds feasible and what can be achieved technologically. A lot of calculations in those stages, very few satellites launched, trying to put everything together. In the period 60s and 70s, there were quite a few experimental satellites and first commercial satellites launched. And in those days, you know, this entire industry, or I wouldn't even call it an industry, entire effort was heavily government subsidized, because in those days the economical resources required to launch any of the satellites were so large that no commercial entity could even put this together. So even majority of governments couldn't put it together. So you had various governments cooperating or jointly, you know, getting the technology necessary to launch the satellites into the orbits. Now, in period 70s and 80s, we started seeing commercialization of these services in a significant way. This was where the satellites were actually launched primarily to support two services. One was the telephony, and the other one was the television broadcasting, and you know, just fixed point links where you would do a television recording in one spot and then relay that and distribute it all around the globe. Now, from 80s to 90s, you had what is called liberalization, where the governments realized that this technology is becoming cheap enough so that they can start getting out of it and letting private entities invest and offer all sorts of different services to satellites. And then we are now in the last stage that is called privatization, where you actually have completely private businesses entering this, private enterprises entering this industry. And one of the biggest ones, as you know, is SpaceX, and it's operating right out of the Kennedy Space Center. They launched just last week the satellite on the rocket.
I think they've launched something today, isn't it?
Yesterday.
Today, right?
Probably
Okay.
not. Yes.
It was
Yeah,
yesterday.
so you can see, I don't know which news you have, but every day there's something, right? So there's a lot of work done on the commercial side. There's Virgin, there's SpaceX, there's all sorts of companies that see that there is a lot of money to be made in space exploration and space launches. What I would like you to, you know, maybe if you have time, there's a link here that I posted, and just a History Channel documentary. It's a little bit old, but it's still good enough to give you a little bit background on how satellites work and kind of some of this information, but maybe from a different angle. Okay. Any questions? So this is as far as introduction. What we're going to start next time is going through the elements of the orbital mechanics, trying to understand how do these structures orbit the Earth and what are some of the laws that